Okay, so moving on from deductive reasoning. We are going to talk about reasoning with algebra, or reasoning in algebra and geometry. And in order to do this, we have to remember some properties that we used in Algebra 1. And these are properties we use to solve equations from Algebra 1. So I'm going to kind of go around this spider web. I'm going to start at the top with substitution, and I'm going to work my way around clockwise. So at the top, if you look at substitution, it says if A equals B, then if A equals B, then B can replace A in any situation. And I want to circle that word replace. Substitution means replace. If two quantities are equal, one can replace the other in any equation. Going down and to the right, multiplication property of equality says if A equals B, then A times C equals B times C. And that essentially says if I multiply both sides of an equation by the same quantity, it doesn't change that equation. Same thing for division. If I divide both sides by the same number, C, that doesn't change the equality. It doesn't change the equation. The only way this does not preserve equality, or the only way it could change the equation, is if C is 0, because we cannot divide by 0. Moving to the transitive property. The transitive property is a little harder to follow. So it says that if A equals B and B equals C, then A equals C. Because if both A and C are equal to B, that means that A and C are equal to each other. Moving on, the symmetric property just says if A equals B, then B equals A. It means with equality, we can write the equation one way or the other. It doesn't change the equality. Reflexive property is pretty easy to follow. Reflexive property says that any quantity is equal to itself. A equals A. And then addition and subtraction are similar to multiplication and division. The addition property says if I add the same number to each side of an equation, it doesn't change the equation. Same way subtraction. If I subtract the same number from both sides of an equation, it doesn't change that equation. It preserves that equality. So these properties are going to be properties we reference quite a bit. So be prepared to come back to this little spider web, this graphic organizer, to reference these when we talk about proving things. So moving down to the distributive property. We use this a lot in Algebra 1. And the distributive property says we use multiplication to distribute a value to each term of a sum or a difference that is inside of parentheses. So with a sum, you do A times B plus A times C. So AB plus BC. With the difference, A times B, A times C. AB minus AC. Now, with the examples I show you with numbers here, it's kind of what you would use in mental math, but it's just saying that if I broke apart, and I could have showed this a little better way, but if I'm multiplying 5 by 24, that's like multiplying 5 by 20 plus 4. So mentally, I break that down as 5 times 20 is 100, plus 5 times 4 is 20. That's 120. So that's the way I tackle some problems in my head using mental math. So if you want to pause the video and try B, you can do that, but I'm just going to jump straight to B. And I'm going to say that 3 times 17 is like 3 times 10 plus 7, which if I distribute, that's a lot like 3 times 10, which is 30, and 3 times 7, which is 21. That's why this is 51. So distribution can be a useful kind of but useful tool to help you simplify some expressions using mental math. Moving to example 1, we are going to kind of create our first sort of proof. So, what usually happens is you're given something, and you have to prove something else. We're going to prove what the value of x is, or show what the value of x is, using what we call a two-column proof. So we start with what's given. AB bisects RAN. If AB bisects RAN, I can say that two angles are congruent. RAB is congruent to angle NAB or BAN, however you want to describe that. And the reason I can say that, so this is all about statements and reasons. This is my statement that these two angles are congruent. My reason is, we talked about this reason earlier in the year, It's the definition of an angle bisector. A bisector creates two congruent angles, okay? And from that, I can say that the measure of RAB equals the measure of NAB. So we talked about that before. Congruent means equal measure. So, oops, that was a G. That should have been a C. Congruent, and I'm going to use the symbol for angles, have equal measure. Okay? So the reasoning with geometry stuff, which is what I just did, is a little tough. So the idea behind this is we can solve an equation for x. We have to set up that equation. The expression that RAB stands for is x. So I'm replacing RAB, measure of RAB, with x, because I know its value. I'm replacing the measure of NAB with 2x minus 75. So if you go back to your properties from the top, the property that talked about replacing something with something else was substitution. So I substituted x for RAB, 2x minus 75 for NAB. That allowed me to write this as an equation. So I'm not going to show the steps to solving, but I'm going to show the result of those steps. So I'll explain what I mean by that in a second. If x equals 2x minus 75, I would start solving this equation by subtracting 2x from both sides. That would create this as an equation if I subtract 2x from both sides. Subtract 2x eliminates it from the right side. X minus 2x is negative x. So the property I used was the subtraction property of equality. And I know I'm doing a little bit of abbreviating here. I'm doing that mostly to save space. Now, if I was going to solve this, I would try to get rid of the negative on that x value, or the value of x on the left-hand side. So I would divide both sides by negative 1. If I do that, I get x equals 75. I divided both sides by negative 1, so that's the division property of equality. And we did what we set out to do. We found the value of x. We just used justifications for each of our steps. That's the tough part about this, is knowing which justifications to use. That's what we will practice today. So moving ahead, and these are properties we already talked about, but they're applied in a geometric sense. Reflexive property says anything that is congruent, or any object is congruent to itself. Okay? Any object is congruent to itself. Symmetric property says congruence can be written two different ways. A can be congruent to B, B can be congruent to A. And then the transitive property says, and it's easier with the angles to explain, but that if A is congruent to B and B is congruent to C, then A is congruent to C. Because A and C are both congruent to B, that means they're congruent to each other. So, below this, completing each statement, we're going to use the transitive property for each of these statements. If P is congruent to R and R is congruent to A, we can assume that P is congruent to angle A. Angle P is congruent to angle A because they're both congruent to angle R. In B and C, it's a little bit different. It's saying that if X is congruent to N and blank is congruent to Y, then X is congruent to Y. For X and Y to be congruent, they both have to be congruent to angle N, using logic, all right? Using logic with that transitive property. And then finally, if L is congruent to T and T is congruent to blank, then L is congruent to Q. So for L and Q to be congruent, they both have to be congruent to angle T. So that's the thinking I use to find which value gets put in the blank. And again, we will practice this as we go, but it's getting down these properties and being able to apply them. So last example, all right, big breath for this one. What we always look at with proofs is that what is given and what we're trying to prove. So in the first statement, the reason we can say this first statement is because it's given to us right at the beginning. We say that that is given. That is our given. The reason we can say AB is congruent to CD is because that is given to us. The reason we can say AB is congruent to CD It's kind of like before when we said two angles that are congruent have equal measure. I'm just going to say congruent segments have equal measure. Okay, congruent segments have equal measure. Congruent means equal measure. We talked about that before. It's just knowing what to say to justify that. Now, the next step is going to be a little weird, but if you go back to the top and you look at our properties we just talked about, BC is equal to itself, or its measure is equal to itself. That's considered the reflexive property. Whenever I say something is equal or congruent to itself, that's the reflexive property in action. Okay? So this is an equation. Okay? This is an equation. So in step 2, we set up that equation, AB equals CD. Saying that BC is congruent to itself allows us to take the equation from number 2 and alter it. And what we did to alter it was we added BC to both sides of that equation. So what the property that we used was the addition property of equality. We added BC to both sides of the equation from number 2. So it's noticing that we added something to both sides of that equation. So in number 5, it's noticing that when I do AB plus BC, and looking up at the diagram, AB plus BC equals AC. BC, I'm going to use a different color for that. BC plus CD equals BD. So if you remember back from chapter 1, that was our segment addition that we talked about from before. That two segments add to equal the entire segment that they make up. That's the segment addition postulate, but I'll just say segment addition. And then, if two segments are equal, that means they're congruent. So that's the definition of congruence. So that's the definition of congruence. Equal segments are congruent. So you're going to need some practice on this. I have a quizzes, I have a paper and pencil practice for you to do both of those and the checkpoint to make sure that you're totally ready to move on and talk about geometric proofs instead of just algebraic proofs. We already did some geometric proofs, but the practice is really going to help with that.